Now, in this classwork, we're really going to be combining kind of all the little things that we've been looking at so far. We're going to be looking at histograms and kind of eyeballing them for their center and their shape and their, spread. We're going to be doing that. We're going to be using our mean and our standard deviation in a sort of context to help us make good predictions or make better predictions. So this classwork, we're going to start taking those individual concepts and tying them all together so that we can actually do something worthwhile with them. So hopefully it may be a little tough because again, we're stringing together different concepts that are already tough on their own. But now you hopefully this is going to start giving us some context of like, okay, how can we use these things to actually do something? Okay, so we're going to begin our discussion on models by reading an excerpt from a textbook called Statistics for the Social and Behavioral Sciences by David Kenny. And this expert is called Testing a Model. So I encourage you while you read to also write down some things you find confusing or any questions you have. And if you're actually writing down, you may want to have two columns or do it on the left hand and right hand side of the page. Um, Writing on the right hand side, your questions or confusing bits, and maybe on the left hand side, notes to help you understand what the author means, right? To when you figure it out, so you can sort of summarize it for yourself on the left and then questions, confusions on the right. Okay. So we are going to be reading this Testing a Model. So, how many times have you wished for one more hour to study for a midterm exam to increase your chance of getting an A? All you needed was that one extra hour of study. But does one more hour of study really make much of a difference? To address this question, a teacher could instruct students to come to a 2-hour midterm exam with their notes and study materials. Then, half of the students would be given an opportunity to study, and the other half would engage in some irrelevant activity, such as watching soap operas. After an hour, they would all take the midterm. The teacher would then see whether those who had the extra hour of study did better on the midterm than those who did not have that extra hour of study. They did not have the extra time. The teacher would know if 1 hour of study makes a difference, or more accurately, how much of a difference. Now, what was just described is a research study. Research can be used to help answer important questions such as the following. Does divorce affect children's social development? Does psychotherapy improve one's mental health? Does television violence make children more aggressive? Does bilingual education retard or slow, that's what that means, retard or accelerate the performance of children in schools? Research is more than, quote, men in tweed suits cutting up frogs paid for by huge government grants, as according to Woody Allen in the movie Sleeper. Research helps us in understanding the world around us. Research in the behavioral and social sciences often involves testing statistical models. So, what is a model? A statistical model is a formal representation of a set of relationships between variables. Statistical models contain an outcome variable that's the focus of the study. In studies of weight change, the outcome is weight change. In studies of psychotherapy, it's adjustment. In studies of education, one often studied outcome is reading skill. In research, the outcome of interest is called the dependent variable. A dependent variable is what is supposed to change in response to changing events. In statistical models, it is written on the left-hand side of the equal sign. Now, the variable that brings about change in the dependent variable is called the independent variable. Examples of independent variables are type of psychotherapy, drug dosage, and age. The dependent variable is assumed to be some function of the independent variable. How the independent variable affects the dependent variable is represented on the right-hand side of the equation, which we'll see a little further down. Sometimes the designation between independent and dependent variable depends on the variables under study and the researcher's theoretical orientation. For instance, researchers study the relationship between self-esteem and academic performance. Some designate self-esteem as the independent variable and academic performance as the dependent variable. Others might reverse those designations. Other variables that cause the dependent variable to vary, besides the independent variable, are represented by the residual variable. The residual variable represents the degree to which the researcher is ignorant about what causes the dependent variable. The residual variable is sometimes referred to as error or noise. In simple equation form, the model is dependent variable equals the effect of the independent variable plus the residual variable. Now, by far, the vast majority of models in the social and behavioral sciences take on this general form. The only major difference is that most models have more than one independent variable on that right-hand side, but the basic specification of the model remains the same. In this model, the independent variable and the residual variable are added together to cause the dependent variable. This is not the only way that the independent and residual variable could combine. For instance, they could multiply. However, an additive formula is by far the simplest and most common formulation. Most of the standard statistical models assume that the effect of the independent variable and the residual variable add together. To better understand a statistical model, consider the following example. A researcher investigating the effect of owning a personal computer on grade point average made arrangements to give a personal computer to each of 30 students. Another 30 students served as a comparison group, and they did not receive computers. 1 year later, the researcher measured the grade point average of the two groups. The independent variable is owning or not owning a personal computer, and the dependent variable is grade point average. The residual variable represents any other causes of grade point average besides owning a personal computer. The residual variable is the way of accounting for the fact that all students with computers or without computers do not have the same grade point average. Statistical models are a bit more complicated than the independent variable and the residual variable causing the dependent variable. In most models, a constant is added to every person's score. So in equation form, we would see dependent variable is equal to some constant plus the effect of the independent variable plus the residual or error or residual variable. In many models, the constant term corresponds to the population mean of the dependent variable. And the residual term is a necessary part of a statistical model. It's also called the disturbance, error, or noise. Okay, so now we'll start taking those components like shape center spread and start putting them together for the purpose of prediction. So we have a histogram here displaying finger length, and this is split into which digit, and then just below it we have some data. So part of what it means to explain variability is to find variables that have relationships to one another. That way, we can use the variability in one variable to say something about what we expect in the other. So in this data that's pictured above, this is related to the finger data like we collected in our classwork 3 on variability. So we see this data is looking at finger length, at frequencies of those finger lengths and split by which digit are they talking about, the thumb, the pointer, the middle, ring, and pinky. So take a moment and considering that data, I want you to try to think, what are the two variables being represented here? And what kind of variable are each of those? Categorical or continuous? So I encourage you to pause the video right here. Try to identify the two variables and whether they're categorical or continuous. Now I've kind of helped a little bit, helped in identifying what those two variables are. Those two variables are finger length and which digit are we talking about? Now frequency, which we see over here, that's not really a variable. That's just saying how many of each of these finger lengths do we have, right? So frequency tells us it's just counting how many. The two variables are finger length and which digit. So if we think about these, and then I'm just going to write digit. So if we think about these, the digit is referring to, I'm going to start there. I think that one's a little easier. Is it referring to, is it a thumb? Is it a pointer finger? Middle? Ring? Or pinky? Right? So in this case, we're talking about these are categories. Which category does each finger measurement fall into? Is it a thumb finger measurement? Is it a middle finger measurement? So these are categories, and so this would be a categorical variable. Now finger length, if we consider looking back up at our histogram, now keep in mind when we're doing a histogram, what kind of data is always being displayed? Well, it's ranges of numbers, right? It's if we're looking at a histogram, we're always looking at frequencies as related to some continuous variable, right? The numbers that we see here are a range of values, and we have all sorts of numbers in between. So if we're talking about a range of values, then that finger length variable, it's not categories, it's numbers, and so that would be continuous. Okay, so these are the two variables we're talking about. Finger length, which is continuous, and digit, which is categorical. Now, imagine that the class that this data came from added a new student. That person is not provided their finger measurements yet. Based on the information shown in the figure in the table, what do you think might be a possible good guess for that person's thumb length, right? So considering what we see for thumbs, if you had to just come up with one good guess, there's a new person's added to the class, what seems like a pretty good guess for that person's thumb length? Let's take a moment, think about that, and write it down. And then I also want you to think about how off do you think our guess might be on average? So, and do you think that we would be exactly right with our guess? So, are we going to be exactly right on that value? Probably not. But there's a certain range of values around that guess, some a little higher, some a little lower, that would probably make sense or be good guesses too. So, what value do you think might help us in determining that kind of good guess range, right? So, if we take our guess, are we likely to be exactly spot on? No. There's probably a pretty good range though where we could, well, it's probably going to fall somewhere around here. So, what values would you use for your guess? And then what might you use to try to help figure out that range? Now, we can use the mean and the standard deviation, hint, hint, look back at your previous one, in a way that is very special. So what is this special statistics method? So this is just kind of little mini lecture time. So we can use those descriptive statistics in a statistical model to infer things about the population of people that these finger measurements came from. So here's the difference. We're no longer just summarizing the data that we have. We want to also predict for a new person, right? So presumably that person comes from, if we have our greater population, and then we've got, randomly sampled people end up in our sample that we use to try to kind of infer, make sense of things, like draw conclusions about our population. So what we're really doing is we're using our sample statistics, right? We can calculate the mean of a sample. We can calculate the standard deviation of a sample. And we're using those to kind of create a model or an idea about this population. So all of statistics is really summarized by this basic idea. So this is really an idea written as an equation. It's not really a formula where you're going to plug in things, but we have some data, and that data we want to think of in relation to our model that we're using. But we also know it's probably not going to be that a model is never going to be 100% perfect. It's never going to capture absolutely everything. So we're also going to see some error, right? So this data is what's happening based on the model, and then sort of the other stuff that's happening too. So we have some real data from the sample. That's our data down here, our values that go towards getting those descriptive statistics. And we're trying to explain something about the population that the sample came from by using a model. But data in the real world are messy, so our model, again, isn't going to predict every or even most or even any of our data points perfectly. There's always some error or noise or other information that isn't accounted for by our simplified model that also affects the real data. That error or noise is what we discussed before as the unexplained variability. It gives us an idea of how off our model is from the whole truth. So in this case, we could form a sort of model like the sample of the, or the, do I mean sample? So if we think about like thumb length in this case, being more specific, talking about thumbs, our estimate for our thumb length, or if we're, trying to summarize that sample of thumb length, then we might start by looking at the mean of the thumb lengths that we see in that sample, and then understand that, there's that bit of error. There's, well, our guess may be a little above, maybe a little below, and so what might be a sort of reasonable value to help us estimate that? We could use in this case, the standard deviation, since that sort of gives us an estimate of the average variation we see around that mean. So in this example, we're using our sample mean to give us an idea of our population mean. Is that going to be right on? Probably not. But that's why we're quantifying our error, how off our population mean is, using the standard deviation as a sort of reasonable range, right? It could be a little higher than that by about this much, a little lower than that by about this much, probably in this comfort range right here. So this isn't really an equation that you would solve for, right? We wouldn't plug in numbers and then find a value and say, this is the answer. It really represents the idea of estimating a real person's thumb length as equal to the thumb length of our sample, which is the information that we have, plus or minus about the standard deviation, right? So in this case, we could estimate based on the mean of thumb length, which if we go back is just about 55, and then use our standard deviation to kind of help us establish that range. Okay, so we have our mean is equal to about 55, and then we're saying kind of to get that range plus or minus about 7.74. So this kind of gives us a range of about from, if we were to do the adding and the subtracting, we would see a range of about 67.25-ish and 60, sorry, did I say 67? 47.25 and 62.75 kind of answer, right? So this might be our range of like good guesses. So we start with the information we have, the mean of our sample, right? We use that to estimate for the mean of our population. We know it's not going to be exactly right on. About how much off do we think we're going to be, or about, where's our wiggle room essentially? It's going to be plus or minus about 7.74. Since we know the data we have on thumb lengths shows that average variability among people in the sample's thumbs is about that much, right? So it's more of an around 55, right? If we're going to predict using this basic model, around 55, but probably within about 47.25 and 62.75 kind of answer. Now, why is this a model? Well, the sample mean is not really the mean of the population, right? And the population is who we ultimately really, really care about. So when we're using this sample mean, it's an estimate of the population. We don't know for sure what the population is. We're just using it as probably it's somewhere around this. So that means it's probably pretty close, and it's definitely better than making a wild guess based on nothing, but it's also probably not exactly right. So I want you to think about what a model in kind of the general sense is used for. Now, a model is often sort of an idealized version of something, or a rough approximation or a simplification of something that's more detailed or complex, right? That's what a model is. You kind of simplify and look at it. What's the basic idea? Statistical models are very much the same. It's a way of approximating for something that's kind of good enough for some purpose. So for example, if I wanted to model the front of my house, I might say it looks roughly like a square. It's really more of a rectangle with a triangle on top. Now, my house actually has all sorts of random parts that stick out, like windowsills and porches. But if I use a sort of like square and triangle model as a simplified rough approximation, right? That's our model. It's a rough approximation. It's simplified. It's getting at the basics. If I wanted to estimate how much paint I would need for the front of my house, a model would probably be good enough. Not exact, but pretty close. So statistical models are going to be useful for us to approximate or estimate for things in the real world, like predicting some new person's information. Now, why do you think that we should use the mean as the basis of our model rather than the median? So thinking back to that classwork 5 that's all about the mean, why do we tend to use the mean in our models rather than the median? What do you think? And then in a related follow-up, why do we include that standard deviation in our model? So you may want to hop over to the discussion board and discuss this if you don't have a clear idea, right? Or bounce ideas off each other. And then I'd like you to think, would our model be better if we added more information to it? So for example, if we knew a little bit more about the new student who is being added to the class, like if the person was tall, or if they're female, or if they're a sociology major, or how big their middle finger is, would that help us? Would some of that information be more helpful than other information? Is all new information, kind of equally relevant and helpful to our model, or is some going to be more helpful than others, do you think? So again, you'll want to ponder, reflect, discuss that, and then note your reflections. Now we have two figures here. So figure 1 on the left shows the thumb lengths for the sample as split by the height median split for the class. So what this means is the class was divided into two categories using the median as the splitting point. So it's like if you have a bunch of, go away, if you have a bunch of data values, right? Let's say they're in order, then we find the median. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it'll be 7 on each side. 1, 2, 3, 4, 7. So it's like if we took a cleaver and we just chop our data into right at that median. That's what a median split is. We're literally splitting it into, now we have like the short half and the tall half. And so that's what's being displayed here in figure 1, is the thumb lengths for people in the shorter half of the class are shown on the top, and then the thumb lengths for people in the taller half of the class are shown in the bottom dot plot. And just as a little side note, when the computer is doing this, right, sometimes it's not always going to be exactly 50-50, just because sometimes right in that middle section, there are several of the same value, and the computer decides, well, am I going to put that down here? Am I going to put that up here? So you may find occasionally that it's not exactly 50-50, but it's really close, and it's based around what is that median value. Now, the figure on the right, figure 2, shows the thumb lengths for the sample, right? Same sample, same thumb lengths, but instead of splitting it into shorter half and taller half, it's split into what major the student is, whose thumb that belongs to. So we have psychology students, sociology students, and anthropology students, each taking a section of this class where the data was gathered. So we can see the thumb lengths of the psychology students, the thumb lengths of the sociology students, and the thumb lengths of the anthropology students on the bottom. So intuitively, I want you to think, which of these two variables, the height median split or major, which one seems to explain more of the variability that we see in thumb length? And it may help to think of it as, which one of these variables do you think would be more helpful for predicting someone's thumb length more accurately? So you may want to take a moment, pause, ponder, discuss. And then let's think about what's going on here. So if we're trying to explain the variability, we're trying to refine our guess, right? We're trying to be more accurate by using some information that we have. So if we look at these two, consider which one seems to help us kind of narrow in or refine our guess the best, right? So in this case, it's actually figure 1, the height median split. So because these two distributions, if we sort of estimate the shape, right, and that one maybe would go out a little more, something like that. So if we estimate those shapes, we can see that they're a little bit different from each other, right? If I wanted to sort of estimate where the center is of this one and the center is of this one, they seem like they might be a little different, right? So this data is clustered, it looks like a little lower. This data is clustered a little bit higher. So is that going to help me sort of refine my guess if I know the person's in the short half or in the tall half, right? Yeah. So this, if I know they're shorter, then I might move my value, move my guess down a little bit based on what I see. If I know they're in the taller half, I might move my guess up a little bit based on that. Now, looking at the major distributions in figure 2, these distributions really are not that different from each other. So they're not really helping us pinpoint or narrow down or revise our estimate based on which major, right? Because psychology, there's a total range where I could guess down here, I could guess a little higher, I could guess up here. There's no sort of like, this is the good guess, right? And if we look at sociology, it's kind of the same thing in anthropology. They're all really spread out. It doesn't really help us sort of focus in on, okay, well, if I know this student is a psychology student, am I going to refine my guess? Well, I don't know. It still seems like probably somewhere around the middle might be a good guess. And so it doesn't really help to think about major. It's not helping to explain that variability that we see, like figure 1, that height median split is. Right? And if we think about intuitively, does this make sense? Yeah, but do we think that being tall or short, it tends to be related to how long your thumb is? Probably to a certain degree. Do you expect people with different majors to have like a certain thumb length, like different thumb lengths from each other? Not really. We would expect shorter people, taller people, all sorts of different people, regardless, like mixed together in the majors. So we can't really say, oh, if you're a sociology major, you have a smaller thumb. And that doesn't make as much sense, right? So based on, I just kind of explained the answer to this one. So based on those dot plots, why do you think that height category explains more variability in thumb length than major? Right? So just try to summarize what I just talked about there with, it helps us to sort of narrow in or refine our guess. We see some differences between the groups that helps us identify, oh, I would revise this way if I know this about them, or this way if I knew that about them. Uh, this one does a much better job of that than this one. So another way of saying explains variability, and again, I think I already answered this one, is that if we added height category to our model, right? So if now we're talking about, it might be like not just the sample mean and the standard deviation, but also are they short or are they tall, right? If we added height category to our model, we would do a better job of predicting someone's thumb length. So if we knew that person was short, how would you potentially revise our original guess? So look back at your data and consider, just for the short half of the class, if you knew that person was short, What value might you choose to be your best guess for a short person's thumb entering the class? Now, how might our model change when we know a little bit about someone's height? Well, we can, like I said, we can add that height category, that height variable, into our model equation, right? So what we might end up doing, we could have like short people, sorry, the shorter half of the class, shorter people's thumb lengths. I might revise my guess by looking specifically at, well, what is the thumb length for, what is the mean thumb length for that shorter half of the sample, that short group? And then it's probably not it's going to be exactly that. I know there's going to be some error. So I could use maybe my standard deviation for that short group or some form of estimating. Again, just there's going to be some sort of error there, right? So, but if I know this person's in that half of the class, then I might look at, well, what's the mean for that half of the class? And then adjust accordingly. Just as if we thought or if we knew it was a tall person's thumb, then we might use the tall sample mean and then some sort of measurement of error for our tall group specifically. Right? So we could add in this where we see, okay, well, are they short or are they tall, and adjust accordingly. Now, so far we've looked at height median split to explain thumb length. So we only had 2 levels of height category, shorter and taller. What if we took it a step further and we split each of those halves into half, right? So if we have, these are the short half and these are the tall half. Well, why don't we split each of those in half? So we have like the really short, the shortest people, and then people who are kind of short, people who are kind of tall, a little taller than that median, and then people who are a lot taller. If we had more kind of categories to help split our data into, do you think that that would help us even further in predicting someone's thumb length in a less wrong manner? What if we split it into 8, right? We split each of these into 8 and we get like the shortest all the way to the tallest split into these different groups. What do you think? Would that help us to predict thumb length in a less wrong manner? So I want you to take some time and think about that and then explain why. Why do you think that? And then this is where we're going to pick up in classwork 8, which is really the second half. This originally was one long classwork, but I split it into 2 shorter ones. So we'll pick up here in classwork 8 and we'll continue with this discussion of models around using finger lengths. And we'll kind of look at some more concrete examples with the data. Okay? So go ahead and finish up your thoughts, and then I'll see you next time.